As the spacing of your stirrups gets larger, your capacity is going to drop. Now, what's so important about that? Well, not that we don't want it to drop. It might be perfectly okay to have it drop.
You have to adjust for it.
Okay. Where in a beam might it be okay to have our capacity drop?
In the center.
Why do you say in the center?
Because your shear capacity is going to run closer towards your support.
You mean your, not shear capacity, your factored shear. I mean, typically what happens is your factored shear, as you get towards the middle of the beam, especially uniformly loaded beams, your factored shear is going to drop off, right? I mean, how many times have we seen the shear diagram, be maximum over the support, go to zero out in the middle? Well, the question becomes, you just have to have a design capacity greater than the shear at a given point on a beam. So if we're designing for spacing over here at the, where shear is very high, do we really need that spacing out here in the middle where the shear is dropped off? The question, the answer to that question is no. I mean, we don't. So it might be okay as we go towards the middle of the beam, it might be okay to have our spacing of stirrups get larger. I mean, that might be perfectly okay. Now, there's some rules that we have to live by, okay? And this is where the code comes in. Now, the way I explain this, I mean, there's a lot of ways as we move towards design of stirrups that a lot of criterion that we have to meet, but I like to think of it as a couple basic, points. And these are code criteria, but nonetheless, let's go over them. I usually say that there's three big code criteria when it comes to shear. The first code criteria is what I call VU critical. The code says that you must design your shear capacity, your beam, in order to meet the critical shear on the beam. Now here's the deal. The critical shear is not necessarily the maximum shear. When we think about real concrete construction, our beams are, at least most beams are going to be monolithically cast into the columns. So typically when we're doing reactions, the reaction that we're actually looking at would be in the center of the column, center of the wall, or whatever. Well, you're not going to. I mean, that could be a big shear force when you consider that, but you're not going to develop a shear crack over the column, are you? Why aren't you going to develop a shear crack right here? Because the column's pushing up on it. A shear crack has to be a tensile type failure. You got this column or this wall pushing up on the bottom of that beam, which is monolithically cast into that wall, into that column. You're not going to develop a shear crack here. Where are you going to develop a shear crack at? As you get out from the column or out from the wall or out from the support. It's going to happen out in here. Well, the code says the critical shear, because of this sort of compression that the support or the column or the wall gives us, the critical shear occurs d, a distance d, out from the face of support. So the code says, don't don't worry about trying to calculate your maximum shear over the support. It's not going to happen. All right? It has to occur out here as you get out from the face of the wall, the column, the support, whatever we're talking about. Okay? And they say as far as the value goes, whatever your shear diagram looks like, let's say it was a normal shear diagram for a uniformly loaded beam, they say come out a distance D, and whatever that shear value is there, that's what we're going to call the critical shear. So you hear or you read the book or you read, a lesson, and people will talk about the critical shear. And basically what they're saying is don't necessarily design for the shear that's going to occur over the middle of the support, because it's not going to happen that way. Design your maximum shear, or the shear you have to generate a capacity for, calculate it, or it is that shear that occurs a certain distance out. Because by the time you get a certain distance out, all that compressive effect from the column, the support, the wall is sort of gone away, sort of dissipated. So that's the first thing the code says. All right, and we'll talk about that more, but they talk about a critical shear. I call that critical shear, just in symbol notation, VU critical. Okay? So that's the first thing that the code talks about, critical shear. The second thing that they talk about is maximum stirrup spacing. Okay? And there's a couple different criteria that they use for maximum stirrup spacing. All right? But I'm going to list them I'm going to give you 3 of them, and then I'm going to tell you which one you always use. All right? The first criterion that they talk about is don't space your stirrups more than half the effective depth. Now there is an exception to this. In very heavily loaded beams, they might say don't space your stirrups any more than a quarter of the effective depth. But again, for our purposes, we'll never see that. So one of their criteria says, hey, no more than half the effective depth. All right? The reason they're doing that is they want at least, as a minimum, at least one stirrup in the line of every crack. Okay? And if you think about this, the crack's going to run from, this is my beam, and I've got steel down here. My crack's going to run diagonally on a 45-degree line, right? Then it's going to split along the steel. So my crack basically looks like this. If this distance here is D, what's this distance here? No, that distance D too. It's a 45-degree line, right? If I say space my stirrups no more than 1/2 D, no matter where that crack would occur, what have I always guaranteed myself? At least one stirrup in that crack. I mean, even if I put a stirrup somehow right here at the beginning of the crack, even if I put one right at the end of the crack, if I always say 1/2 D, I always got to have one somewhere, at least one somewhere along that crack. So that's what that means. The other 2 concepts are really minimum steel. You remember with longitudinal steel, we talked about row minimum and having a minimum amount of steel just for ductility. They sort of do, it's the general same concept in stirrups. They got 2 other formulas. AVFY divided by 50 times B. You know what AV is, you know what FY is, you know what B is. Okay? The other formula they use is AVFY divided by 0.7 square root of F prime C times B. These are sort of minimum steel, ductility type related criteria. This one's just put one stirrup in every crack. The easiest thing to do is calculate all three of these all the time. And you'll choose the smallest as your maximum spacing. Okay? So the easiest thing to do, I think, when you're approaching, whether it's an evaluation or a design, you want to know how big can your stirrup spacing get, calculate all three of them, choose the smallest. Okay? I'm not saying when you get into design you have to use the maximum. I'm just saying that's the easiest. In design, you always want to make sure you know what the maximum is, because you don't want to go over the maximum. Okay? So that's that. Okay, does that make sense? Okay. The last code criteria that you want to know as you go to starting to look at evaluation or even design, the last one is what I call no stirrups. Now this is different from maximum spacing. Maximum spacing means when you're spacing stirrups, what is the maximum spacing I can use? I don't want to go over the maximum, but what is the maximum? No stirrups means, is there a place where you don't need stirrups anymore? Now just in general, if there was such a place in a beam, where do you suppose that place would be?
Shear zero.
Yeah, where shear's very low, where shear's approaching zero. I mean, maybe shear in our beam gets so low that I don't need stirrups anymore. Where would that place be? Yeah, around midspan, where that shear diagram is going down towards zero. Okay? There is a place out there, generally speaking, could be a place where you don't need stirrups. You do not need stirrups where the shear gets very low, where VU gets lower than this value, phi VC over 2, or 1/2 phi VC. If you took away stirrups, you'd have no VS. Your whole capacity then would be phi VC. They're cutting it in half and saying when you get past that point, you don't need stirrups anymore.